This is the second part of lecture 10. So in this part we uh, prove the main theorem. Uh, the main theorem is following. So it says that if both the partial derivatives, okay, both the partial derivatives are d r f and dkf exist in an open ball b c comma delta, which is equal to uh, the set of all points x belongs to Rn, such that norm of x minus c is strictly less than delta. Okay, and if both are differentiable at c, okay, then uh, the two partial mixed partial derivatives dr comma k f at c and dk comma r f at c are equal. Okay, so this is the main theorem. So we prove this theorem here. So prove. So let f1 and so on fk sorry this is m. So suppose these are the component functions of f. So that is f equal to f1 and so on fm. Then d, the rth partial derivative of f, this is equal to d r f1 and so on d r f m and d k comma r f, this is equal to d k comma r f 1 and so on d k comma r f m. So therefore d k comma r f at a point c equal to d r comma k f at the point c if and only if d k comma r f j at c equal to d r comma k f j at c for all j equal to 1 and so on m. For every j, if j is real valued, and therefore to prove the theorem, therefore to prove the theorem, it suffices to prove the theorem for real valued function. So it suffices to consider m equal to 1. So thus we simplify the theorem. So this is page number 6. Moreover, there are, so furthermore, so only two variables are involved in the theorem, that is rth and kth variable. So furthermore, only two variables are involved in. Therefore, it suffices to consider n equal to 2. It suffices n equal to 2. Thus we consider f is a function from R to R. Okay, and for simplicity, and we consider the point C is equal to the origin 0, 0, and for simplicity assume C equal to 0, 0. Okay, so what are the given conditions here? So first condition is D1 F and D2 F exist on open ball with center at C, that is 0, 0. So let us write it as 0, 0, delta, where delta is sum, where delta is greater than 0, a real number. Okay, and the second condition, so the second condition is D1 F and D2 F are differentiable at the point C, and C is equal to 0. This is differentiable at 0, where 0 is the order pair 0, 0. Therefore, we shall prove. So what to prove? We shall prove D1, 2 F at 0, 0 equal to D2, D2, 1 F at 0, 0. This is what we have to prove. Okay. So let us draw a picture. This is R2, and here we have origin, and suppose this is the open ball of radius delta. Okay, so this is delta. Now consider, so take some h greater than 0 such that the square with vertices at 0, 0, h, 0, h, h, and so there are 4 vertices 0, h contained in B 0, delta. So take some h, so that the square, so suppose this is h, this is h, h, so this is 0, h, and sorry, h, 0, and this is 0, h. Okay, so consider such h, so such h should satisfy h less than, of course, delta, and greater than 0. Okay, now So let's go to the next page, page number 5. Now consider capital delta of h. This is equal to, let's say, f h comma h minus f h comma 0 minus f 0 comma h plus f 0 comma 0, and so we show delta h over h square as limit h tends to 0. This is equal to d2 comma 1 f 0 comma 0, and this is equation capital A, and limit h tends to 0 delta h over h square equal to d1 comma 2 f 0 comma 0. This is B. Okay, so if we can prove these two equalities, these two equations A and B, and then it will follow that d2 comma 1 f at 0 0 equal to d1 comma 2 f at 0 0. Okay, so let us prove A. Proof of A. So we define g of x equal to f x comma h minus f x comma 0. Okay, then g of h minus g of 0. Okay, so g is a real valued function. G is from R to R. So we define this by this equation. Now g of so this is differentiable. Okay, so g of h minus g of 0. So what is this? This is equal to f h comma h minus f h comma 0 minus f 0 comma h minus f 0 comma 0, and this is equal to delta h. Fine. Now applying mean value theorem, we have g of h minus g of 0. This is equal to h times g prime of x1, where x1 lies between 0 and h. Okay, and what is g prime of x1? That is so here is the function g of x. So g prime of x1 that is equal to the partial derivative of the first partial derivative of f at x1 comma h minus d1f at x1. Now, okay, so next page, page number 6. So now note that by condition, so condition 2. So by condition 2 we have d1 f is differentiable at 0 comma 0. Therefore d1 f at x1 comma h, okay, this is equal to d1 f at 0 comma 0 plus d 1 comma 1 f at 0 comma 0 acting on x1 plus d 2 comma 1 f at 0 comma 0 acting on h plus norm of this quantity plus norm of this means x1 square plus h square whole power half times some epsilon 1 of h, okay, and again d1 f at x1 comma 0, this is equal to d1 f 0 comma 0. So we are using this condition d1 f is differentiable at 0 comma 0. So by the definition of derivative of d1 f at 0 comma 0, we have this equation and this one plus d 1 comma 1 f at 0 comma 0. So this is the derivative of, okay, d1 f, okay. So the first component, this is x acting on x1 plus second component is 0, so we will not have such a component in the next equation, and plus norm of this quantity that is mod x1 times epsilon 2 h for some epsilon, so small function in h, okay, where epsilon I h greater than 0 h greater than 0, okay, or I equal to 1 and 2. Now uh, now delta h, and this is equal to g of h minus g of 0. So applying mean value theorem, so this is equal to so this is equal to, here we have h times g prime x1, so h times d1 f x1 comma h, so this is equal to the difference of, so let me write h times the difference d1 f at x1 comma h minus d1 f x1 comma 0. So okay, so by this two equality, so we have so we have this is equal to h square d2 comma 1. So here we have one h and it will be multiplied with this h, so h square d2 comma 1 f at 0 comma 0, okay, plus epsilon h, where epsilon h equal to where epsilon h equal to uh, h times this quantity, h times x1 square plus h square whole power half epsilon 1 of h minus uh, h square, so mm, minus so this is h times x1 mod, okay, and times epsilon to h, okay, and okay, so this is, and remember that x1 lies between 0 and h, okay, so this is strictly less than or less than equal to, you may write it less than or equal to h square epsilon 1 h, okay, epsilon 1 h minus h square epsilon 2 h, and this implies limit h tends to 0 epsilon h over h square equal to 0, because limit h tends to 0 epsilon I h as limit h tends to 0 epsilon I of h equal to 0 for all I equal to 1 and 2, okay. Therefore what we have, so page number 7, so what we have, delta h over h square equal to d2 comma 1 f 0 comma 0 plus epsilon h over h square, okay, okay, let me rewrite this, epsilon h over h square. Now limit h tends to 0 delta h over h square equal to d2 comma 1 f 0 comma 0, this term is independent of h, plus limit h tends to 0 epsilon h over h square, and this is equal to 0, so this is equal to d2 comma 1 f 0 comma 0, so limit h tends to 0 delta h over h square, okay, so this is equation A. So equation A is proved. Now applying same procedure on the function, same procedure on the function h of y equal to f h comma y minus f 0 comma y in the place of g, in the place of g, we can find that limit h tends to 0 delta h over h square equal to d 1 comma 2 f at 0 comma 0. So this is equation b. So equation a and b together, a and b together imply that d1 comma 2 f at 0 comma 0 equal to d2 comma 1 f at 0 comma 0. Okay, so this completes the proof. So that's it.